Welcome back for another video in the OpenStax Volume 1 Calculus series. In this video, we're going to be talking about one of the most important theorems in calculus and the study of real analysis, the study of our real number system. That is the mean value theorem. As one of my professors called it, the most valuable theorem. Why is it so important? Well, there are many applications that use the mean value theorem directly, but it is also used in the proof of the most major theorems in calculus. Without the mean value theorem, we wouldn't get to the fundamental theorem of calculus. So the mean value theorem is important not just in its own right, but because it is a foundational theorem on which many other important results are built. The idea of the mean value theorem is relatively straightforward. It does have conditions, namely two. As you might have guessed, since this is often a condition of many of our theorems, function needs to be continuous over an interval, a closed interval, which means continuous from the right at the left endpoint A and continuous from the left at the left or right endpoint B. It also needs to be differentiable on the open interval between A and B. So we can draw the graph without picking up the pencil. It's continuous. Function exists, two-sided limit exists, and they're equal, and it's differentiable. That means we do not have any corners, cusps, or vertical tangency points anywhere on the interior of that interval. Provided these two conditions are met, then we can apply the mean value theorem. The idea is simple. Take the two endpoints and connect them with a line. That's the secant line cutting through the graph. That secant line has a slope. The mean value theorem says that as long as it's continuous and differentiable, then somewhere between A and B, there's a point C where the slope of the tangent line, the derivative, is equal to the slope of the secant line. In other words, somewhere in that interval, you have a point where the derivative, the slope of the tangent line, equals the slope of the secant line. Now, when we think about this, what are some of the things we can prove with it? Well, we can prove that if we have a function whose derivative is 0 over the entire interval, that in fact the function must be a constant. This is a direct result based on the mean value theorem. We have another corollary, a mini theorem based on a major theorem that we can prove from the mean value theorem, which states that if I have two functions, f and g, and their derivatives are equal, and the only difference between the functions is a constant, like +5 or -3. If their derivatives are equal, then they have to be a vertical shift or translation of one another. Now, what else can we do with the mean value theorem? You'll be interested to know that we can also tell when a function is increasing or decreasing, going up or coming down, without looking at the graph. The mean value theorem makes this possible. It says that if the derivative is positive over an interval, the function is increasing on that interval. And if the derivative is negative over an interval, the function is decreasing over the interval. From a practical standpoint, one of the things that the mean value theorem does is it allows the police to give you a ticket when you were speeding on a tollway without actually having to catch you in the act. Let's see how this happens. I'll share my screen with you so we can get started. As part of our work in this theorem, we're going to be learning first about something called Rolle's theorem. Now, Rolle's theorem is actually the mean value theorem in a particular case, a special case, where the two endpoints of the interval, the y values, are equal to one another. If the y values are equal, then the secant line must be horizontal. which tells us by Rolle's theorem that somewhere between A and B, there has to be a point where the derivative is 0. Now, this is important because those are the locations of possible extrema. It's not guaranteed, but when the derivative is 0, we know we have a critical point. Let's look at the learning objectives. We're going to start with this special case, which is Rolle's theorem. And then we're going to move on to the mean value theorem. And then we'll talk about the 3 corollaries that I mentioned in the introduction again. Let's go ahead and look at the statement for Rolle's theorem. What Rolle's theorem states is that if you have 2 points on a graph for an interval from A to B, and the function value at A and the function value at B are equal, as in all 3 of these pictures, then somewhere between A and B, there is a point C where the derivative, slope of the tangent line, is 0. In the first case on the left, you can see it's occurring at a relative maximum. And in the case in the middle, it's occurring at a relative minimum. In this third case over here, we see that it's occurring twice at a relative max and a relative minimum. In other words, the theorem guarantees at least 1 point, but there could be more than 1. Now, again, this is what we would call an existence theorem. It tells us the point C exists, but it doesn't tell us how to find it. Let's take a look at the formal statement. Rolle's theorem has 3 conditions. The first condition is that the function must be continuous over the closed interval from A to B. That means continuous over the open from A to B, continuous from the right at A, and continuous from the left at B. It must be differentiable over the open interval from A to B. Remember, the derivative is a 2-sided limit, and you're not considering differentiability at A and B because we're not looking outside of A to B. The third condition is that the function value at A and the function value at B are equal to each other. Then the conclusion of Rolle's theorem is that there's a point C, which is between A and B and not equal to A or B, where the derivative is 0. If these 3 conditions are not met, if even one of them fails to be true, then Rolle's theorem is not guaranteed. It may still be true, but it's not guaranteed. Do not use a theorem if the conditions are not met. Remember the 3 conditions: continuity over the closed, differentiability over the open, and f of A equals f of B. Let's look at an example where Rolle's theorem does not apply because it fails to meet a condition. This would be the absolute value of x minus 1. You can see it's just been shifted down 1. In fact, it doesn't need to be shifted down, but I guess they felt like it would be fun to do it this way. Notice that it is a continuous function because we can draw it without picking up our pencil. Function exists at every point. The 2-sided limit exists at every point, and they're equal to each other. However, it fails to meet condition 2, differentiability. We have a corner here when x equals 0. Because it fails to meet a condition, we cannot apply Rolle's theorem. It does meet the third condition. F of -1 is 0 and f of 1 is 0. But it failed to meet one of them. Notice that, in fact, Rolle's theorem would not work in this case. There is no point between -1 and 1 where the slope of the tangent line is 0. The slope of the secant line connecting -1 and 1. Let's now look at example 1. We want to verify that this function, the parabola 2x squared minus 8 times x plus 6, defined over the closed interval 1 to 3, satisfies the 3 conditions of Rolle's theorem. Then we'll find all the points C guaranteed by Rolle's theorem. Let's take a look now at the three conditions. Condition 1, continuity on that closed interval. In fact, it must be continuous because it's a polynomial. Make sure that you mention the reason that it meets this condition. Polynomials are continuous everywhere. Condition 2, it must be differentiable on the open interval from 1 to 3. And in fact, the same reason applies here. It's a polynomial function. Polynomials are not only continuous everywhere, they're also differentiable everywhere. That's why they're our favorites. You gotta love them. Defined everywhere, continuous everywhere, differentiable everywhere. And as we'll discover at the end of this semester, we can also integrate them everywhere. Last condition for Rolle's theorem is that f of 1 equals f of 3. For this one, we actually have to do some work. To find f of 1, we substitute 1 in place of the variable. When we do this, we end up with, well, if I'm not mistaken, 0. It's not required that it be 0. It's just required that f of 1 and f of 3 are the same value. Now let's find the value when we substitute 3 in place of the variable. This gives me 18 minus 24 plus 6, which is also equal to 0. Therefore, the third condition is met. This guarantees by Rolle's theorem that there is a point between 1 and 3 where the slope of the tangent line, the derivative, is 0. Let's go ahead and see if we can find it now. To find it, we want to take the derivative of the function, which gives us 4x minus 8, a linear function. We know that f prime of c has to be equal to the slope of the secant line connecting f of 1 and f of 3. Because they're equal, the slope of that line is 0. Thus, we know that f of c, which is equal to 4 times c minus 8, must be equal to 0 as well. This implies that 4c minus 8 equals 0, and that tells us that the value where this occurs is at 2. We're guaranteed by Rolle's theorem that at the value x equal 2, we must have a horizontal tangent line. We don't know whether it's a maximum or minimum. We'll be studying that more in depth in the next section, where we look at the first derivative and second derivative test. Let's now move on to the mean value theorem. I didn't actually prove Rolle's theorem for you, but you can find the proof for it in the textbook. If we look at the textbook's proof, we can talk through it just a little bit here. The proof says, let k be the y value for f of a and f of b. In our last example, it was 0, but it's not required that it's 0, just that the endpoints have the same y value. We'll call it k. There are 3 cases we need to consider. First, that the function is k for all the values in the interval between a and b. That means it's basically a horizontal line. In case 1, if f of x is k for all those x, then the derivative is 0 for all those x, since the slope of a horizontal line is 0. Case 2 tells us that there's an x value between a and b, where the y value is greater than k. In other words, somewhere it goes above the location of f of a and f of b. In this case, because it's a continuous function over the closed bounded interval, we can apply the extreme value theorem, which tells us there has to be an absolute maximum. There also has to be an absolute minimum, but because our y value is above k, we're looking for an absolute maximum. That tells us that there's a point between A and B such that f of x is greater than k, then that absolute maximum must be greater than k itself. In that case, the absolute maximum is not occurring at either endpoint. Remember the extreme value theorem, we look at the endpoints and the critical points on the inside. Because f of a and f of b are k, and we have a function value bigger than that, the absolute minimum can't be at the endpoints. So it's got to be at a critical point on the inside. This is an interior point between a and b. And since it has a maximum there and it's differentiable there, by Fermat's theorem, the derivative at that point must be 0. The third case is if we have a point x between a and b where it goes below the value of k. In this case, we repeat case 2, but instead of looking for an absolute maximum, we look for the absolute minimum. The proof is very similar. Now that we've discussed the proof for Rolle's theorem, let's move into the mean value theorem, which is really the focus of our work here in this section. In Rolle's theorem, we were looking at continuous functions that were differentiable and that met the condition that the endpoints had the same y value. The mean value theorem generalizes Rolle's theorem by removing the third condition. It's no longer necessary that the function value at A and the function value at B be equal to each other. This means that we could have a slanted secant line connecting f of A and f of B. The slope of that line will no longer be 0. The mean value theorem only requires continuity on the closed interval and differentiability on the open. It still guarantees that there is at least one point C in the open interval A to B where the slope of the secant line and the slope of the tangent line are equal. We can kind of think of the mean value theorem as a slanted version of Rolle's theorem. In fact, Rolle's theorem is more a horizontal version of the mean value theorem. The mean value theorem is more general. Rolle's theorem is just a special case of it. In this picture here, you can see that we have a function in blue. This function is y equal f of x. We have f of a here at a, f of a on the left, and we have the point b, f of b over here on the right. Notice that when we look at what connects these two, we have a secant line. This secant line has a slope. And the slope of that line, there must be a point between A and B where the slope of the tangent line is equal to the slope of the secant line. Again, this is an existence theorem, so it tells you it exists, but it doesn't necessarily tell you how to find it. The best way to do this is to kind of eyeball it. Put your pen on the left side and move it along just tangent to the curve until you reach a point where the two lines are parallel. This occurs, in fact, twice for this particular function. We have a C1 here and a C2 here. We're only guaranteed that it happens once, but it can happen more than once. Let's go ahead and take a look now at the formal statement of the mean value theorem. The mean value theorem says, let f be a function that is continuous over the closed interval a to b and differentiable over the open interval a to b. First two conditions of Rolle's theorem. There is no third condition. The conclusion, then there exists at least one point C between open A and B, such that the slope of the tangent line, f prime of C, is equal to the slope of the secant line, the difference quotient, f of B minus f of A over B minus A. The proof follows from Rolle's theorem. We'll use Rolle's theorem to prove the mean value theorem. In terms of history, Rolle's theorem came first and the mean value theorem came later. In order to prove it, what we're going to do is we're going to look at the line that connects the two endpoints. The slope of that line is given by our difference quotient that you see here. The point A f of A is also on the line, as well as B f of B, but we're going to use the point A f of A. Because this is a point on the line, and this is the slope of the line, which we can write as MSEC for secant line, we can use the point slope form of a line to write it as y minus y1 equal to the slope of the secant line times x minus x1. Our x1 can be A, and our y1 can be f of A. This allows us to then rewrite it in the form that you see here. Y minus f of A times the difference quotient times x minus A. We can solve for the y value on the secant line by moving the f of A term to the right side, which gives us the y value on the secant line. We're going to actually define a new function, g, in terms of the secant line and the original function f. Remember, the original function f is doing something like this, and the secant line is slanted. We're going to let g of x be the difference in the y values between the function f and the secant line. Let's take a look at a picture that will make this a little bit clearer. When we look at this picture, g of x, the y value on g, is given by this vertical distance between the function in blue and the secant line in orange. But g is actually going to be, of course, down here. What's graphed in this bright blue is the function g of x. We can write our formula for g of x using the formula for the y value on the secant line, which gives us this expression here. It's kind of complicated, but it's mostly algebra at this point. Notice that at the points where the secant line and the function itself connect, g of x is 0. These are x-intercepts on the graph of g of x because there's no vertical distance between the two functions. Now let's go ahead and see if g of x meets the conditions of Rolle's theorem. Remember, there are 3. We'll start with condition 3. Look at x equal a and x equal b, the two endpoints of our original interval. Notice that at these two endpoints, the secant line and the original function connect, so g of x has an x-intercept there. That means that f of a and f of b are both equal. In fact, they're both 0. That meets condition 3 for Rolle's theorem. We know that our function f is differentiable over the open intervals from a to b. If we look back at our definition for g of x, if this is a differentiable function, we know that the difference quotient is simply a constant number. And we know x minus a is differentiable, and f of a is also a constant number, which means we have the difference of two differentiable functions. So g must also be differentiable. What about continuity? The last condition for Rolle's theorem. We know f of x is continuous by the original. We know that the difference quotient is a constant, and x minus a is just linear. It's definitely continuous because it's a polynomial. And f of a is also a constant. The difference of two continuous functions is continuous, so we know that g of x also meets the third condition for Rolle's theorem. Since it meets all three conditions for Rolle's theorem, then the conclusion must also be true. There's a point C between A and B such that the derivative at C must be equal to the slope of the secant line connecting g of A and g of B. That line, the secant line, is right here. It's horizontal, so the slope is 0. Now we can take the definition of the derivative and apply it to our defined function for g. This gives us the derivative of a difference, which we know is the difference of the derivatives. The derivative of f of x is f prime of x. When we look at the second part, realize that what we have here is something like slope of the secant line, which is a constant, times x minus a, which is a constant, plus f of a, which is also a constant. When we take the derivative of it, the only variable is the x inside the parentheses. That means that when we're done, the derivative of this becomes simply the slope of the secant line, which is the difference quotient. Now we know from Rolle's theorem that the derivative at C must be equal to 0. And because it must be equal to 0, that means that these two terms must be equal to each other. That means that somewhere at C, on the original function f, not g, the slope of the tangent line is equal to the slope of the secant line connecting the two endpoints. Let's talk about a real-world application of the mean value theorem. You may have wondered in the past how it is that if you're traveling on a toll road, you can get a ticket without ever seeing a police officer and no radar guns. Well, let's think about it. When we're driving, we know that position is a continuous function. I can't get from one toll booth to the next toll booth without traveling the entire distance between. I have to be able to draw that path with a straight line, well, assuming the road is straight, but with a continuous line going from one toll booth to the next. I can't beam from one toll booth to the next one. So we know the position function is continuous. Remember that the derivative of position is velocity, which means that I have a differentiable function as well. Since it is both continuous and differentiable, that tells the toll booth operators that if your average speed between toll booth A and toll booth B is higher than the speed limit, then at some point between toll booth A and toll booth B, your velocity, your speed was higher than the speed limit, and you'll get a ticket in the mail. Let's take a look at example 2. Example 2 is a typical physics application of the mean value theorem. Suppose a ball is dropped from a height of 200 feet. Its position at time t is given by the equation -16t squared plus 200. Find the time t when the instantaneous velocity of the ball equals the average velocity. Well, let's go ahead and draw a picture, since those always help when we're doing word problems. Looks like I'm on a hill because my ground kind of got slanted there. I know my building is 200 feet tall, and somebody's standing up here at the top, and they dropped a ball, which is falling straight down. At some point, it hits the ground. How do I find the average velocity? Well, the average velocity would be the slope of the secant line connecting the point, the height, 200, with the point on the ground, 0. We need to find the time at each of these locations. The time when the ball is released is 0, and we know at 0, the height of the ball is 200 feet. We need to know at what instant it hits the ground. In other words, we need to know when S of t is equal to 0. What is that time? In order to find that, we take S of t and set it equal to 0 to find when the ball hits the ground. This means negative 16t squared plus 200 equals 0. Moving the 16t squared to the opposite sign, and then dividing both sides by 16, I have t squared equals 50 divided by 4, which, well, depending on how you want to work it, I guess you would go ahead and reduce it to 25 over 2. Now we can take the square root of both sides of the equation with a plus or minus on the non-variable side. However, we know that time must be strictly positive, and this gives us 5 divided by the square root of 2. Time is greater than 0, so the only time we're interested in is 5 divided by the square root of 2. So I know, for example, at 5 divided by the square root of 2, the height of the ball is 0 feet. I need to find the average velocity. Recall that velocity is the change in position with respect to time. That's basically the difference quotient. My average velocity, the average, is given by the position at time 2 minus the position at time 1 divided by the change in time. This would give me units of feet per second or miles per hour, which we know are velocity units. Not the instantaneous velocity, which is the derivative. It's the average velocity, which is the difference quotient. We know that S of the second time is going to be 0 feet. And we know that initially it's at 200 feet. Make sure you line up the times with the appropriate distance. This is going to be 5 over the square root of 2 seconds minus 0 seconds. This is going to give me a negative 200 feet divided by 5 over the square root of 2 seconds. That gives me feet per second. The denominator of the denominator moves to the numerator. So I will end up with 200 divided by 5, which would be 40, negative 40 times the square root of 2 feet per second. This is the average velocity of the ball as it falls from the roof to the ground. That's average speed. Now, because we know that position is both continuous and differentiable, we can apply the mean value theorem. The mean value theorem says that at some point, the instantaneous velocity had to be equal to that average velocity. Let's rewrite our equation again. S of t is equal to negative 16t squared plus 200. Let's go ahead and find the instantaneous velocity by taking the derivative of the position function. This leads to negative 32t. I need to find the time when this is equal to negative 40 square roots of 2 feet per second. In this case, I need to set the two equal to one another and solve for the time. This gives me negative 40 square root of 2 feet per second equal to negative 32 feet per second. When I look at this, I want to go ahead and simplify and isolate the t. This is going to give me t is equal to negative 40 square roots of 2 divided by negative 32. The negatives will cancel, and I can get 40 divided by 32 are both divisible by 8. So the time when they're equal turns out to be 5 square roots of 2 over 4. This is the time when the instantaneous velocity and average velocity are equal. That's also the reason you get a ticket on a toll road. Let's go ahead and apply the mean value theorem now to example 3. We are going to graph the function, and we'll draw the secant line that connects the endpoints over the interval -1 to 1. And we want to estimate the number of points C where the slope of the tangent line equals the slope of the secant line. In order to apply the mean value theorem, we have to check the two conditions. Is this a continuous function over the closed interval? Yes, because it's polynomial. Is it a differentiable function over the open interval? Well, in fact, it's differentiable everywhere. So we know we can apply the mean value theorem. Let's go ahead and figure out, based on the graph, how many values of C we think there might be. I've gone ahead and graphed it for you. So let's look at the graph. You can see that here is our cubic function increasing over its domain. I've plotted the endpoints, -1, -4, and 1, 6. Then I found the equation of the secant line connecting those two endpoints, graphed here in the dashed purple line. If I take my pen and I put it on the graph, count the number of times you think the slope goes parallel, right about there, to the purple line. Right about there. I think there are 2 points in that region where the slope of the tangent line will be equal to the slope of the secant line. If we're going to solve this problem, how would we know for sure where it was? In order to do that, we would have to compute the slope of the secant line and the derivative and solve to find our C's. We can go ahead and do that now. Remember that the function is a cubic, and at the endpoints, we end up with the following values. This ends up being -4, and when we substitute 1 into the original function, we end up with 6. This gives us the two ordered pairs, -1, -4, and 1, 6. To find the slope of the secant line, we can use the difference quotient, which gives us 6 minus a -4 divided by 1 minus a -1. This gives us 10 divided by 2, or a slope of the secant line of 5. We need to find the points. We estimated there were 2, where the slope of the tangent line is 5. To do that, we'll take the derivative of our original function. We get f prime of x equal to 9x squared plus 2. I want to know when I have a value of the derivative of 5. This tells me f prime of c, which is 9c squared plus 2, must equal 5. Solving for c, I get 9c squared equal to 3, or c squared equal to 1/3. It looks to me like it must occur at plus or minus 1 over the square root of 3. And in fact, those are the two locations that we found. Let's now take a look at example 4. Example 4 is very similar, but with a trig function. Go ahead and pause the video, work it out, then turn it back on, and we'll compare our results. This problem would be more difficult to actually compute the c values, though it is possible. When we look at the graph, notice that it's only being graphed between negative 1.5 and 1.5. Notice that the secant line connects the two. All I'm expecting students to do is graph the tangent over the closed interval and hand draw a secant line. Now take your pen and put it on the graph of the function and stop when you think the slope of the tangent line is parallel to the slope of the secant line, about there. And again, about there. Again, I estimate that there are 2 places where the slope of the secant line is equal to the slope of the tangent line. We're not going to solve this one for the actual location since the mathematics would be more difficult. We'll save that for ones where it's not quite so complicated. Let's move on now to the next example, example number 5. We want to look at example 5 and determine the intervals, if any, over which we can apply the mean value theorem to this function 1 over x cubed. Remember, the conditions are it must be continuous and differentiable. We know that to be continuous, the function must exist. This does not exist at 0, so 0 is automatically taken out. However, the function is continuous everywhere that it's defined. It's defined over the interval from negative infinity up to 0, and again from 0 to infinity, but leaving out 0. Is it differentiable there? Yes. Rational functions are continuous and differentiable on their domain. So we could apply the mean value theorem on either of these 2 intervals, but not over any interval that included 0. Let's take a look at the graph and see why this might be occurring. If we look at the graph, oops, looks like I've got the wrong one graphed there. It's supposed to be x cubed. Let me replace that with a cube. And we'll turn it on. Again, you can tell that it is neither defined nor continuous nor differentiable at 0. I'm going to return this to 2 since I probably had it in there for a reason. Let's take a look at the next one. Over what intervals could we apply the mean value theorem? We know that natural log has an argument that is always strictly positive. The argument is 3x minus 5. So we take 3x minus 5 and set it greater than 0. Solving for x, this gives us that it must be greater than 5/3. The function is only defined on the interval open 5/3 to infinity. Is it continuous on that interval? Yes, it is. Is it differentiable? Yes, but not at, well, we can't establish continuity at 5/3. So we would have to go just to the right of 5/3 to apply this particular mean value theorem. Let's take a look now at the next one. So I guess if I were going to write down the previous one, I would say any interval where the left endpoint is greater than 5/3. I can't use 5/3 because it's not continuous at 5/3. It's not defined there. So the left endpoint must be larger than that. But there are infinitely many numbers larger than that. Let's take a look now at example 7 and example 8. And in example 7, we want to show that there is no C over the interval -1 to 1, where the slope of the tangent line equals the slope of the secant line. Why does this occur? Well, we need to start with the conditions of the mean value theorem. Is it continuous over that interval? This is a rational function, 1 over x squared, which we know is not defined at 0. We can only apply the mean value theorem from some subinterval between -infinity to 0 or greater than 0 to another number. We cannot include 0 because the function's not defined there, which means it's not continuous there. This is why the mean value theorem does not apply. And you can see again that we lack continuity and differentiability on the interior of the region. Let's look at example 8. Example 8 is asking the same question. Why does the mean value theorem not apply over the interval from -1 to 1? The function has a domain of all reals because we have the absolute value of x under the square root. We'll force all of them to be non-negative. The domain is all reals. It's defined everywhere. It's defined everywhere. Would there be a break in the graph? Let's take a look at the graph of this one so that we can see why we do not have the mean value theorem applying. This one sort of looks like the way a child would draw a bird when they're in elementary school. It almost looks like 2 square root functions back to back. And in fact, that's what it is. We have the square root of x if it's positive, and we have it reflected across the y-axis if it's negative. At the origin, we have a cusp. In fact, from both directions, the tangent line is going vertical, producing a cusp at the origin. The derivative does not exist there, even though it's continuous there. It is not differentiable there. That is in the interval from -1 to 1. That's why we cannot apply the mean value theorem. There are some corollaries of the mean value theorem. There are 3 of them. We mentioned these in the introduction to this section, but let's go over them again. We know the mean value theorem is important in its own right, but also because of the theorems that result from it, the theorems that can be proved using it. One of the first things is that the derivative of any constant function is 0. And the mean value theorem allows us to prove the converse. If the derivative is 0, then it must be a constant function. Let's take a look at the corollary now. Assuming that the function f is differentiable over an interval I. Notice they didn't say anything about continuity. Why was it not important to mention continuity? We are applying the mean value theorem. Well, remember, if it's differentiable, it must be continuous. So saying the function is differentiable implies continuity. If the derivative equals 0 for all the values in the interval, then the function must be constant for all the values in the interval. Let's take a look at this particular graph here. This is a piecewise defined function, and I've graphed both the piecewise defined function and its derivative on the same graph. On the first piece, from negative infinity to 0, the graph of the function is cosine or sine. Looking at the black graph, the derivative of that would be cosine, which is graphed in red. On the second piece, notice that we have a horizontal line segment. The slope of that line is 0, so the derivative sits on the x-axis. On the right side, I'm trying to remember, I believe I did a reflected square root function. And you can see that as it approaches 4 from the right, the tangent line must be going vertical because we have an asymptote in the graph of the derivative. Corollary 2 refers to two functions whose derivatives are equal. In other words, I have a function f and another function g that may not be equal to each other, but the derivative of both functions is the same. Mean value theorem can be used to prove that the difference between f and g must be only a constant. In other words, f is g shifted up or down, and g is f shifted up or down. Let's take a look at a graph which shows this. In this graph, I've graphed the function f in red and the function g, which is f of x minus 3, in black. The derivative of both functions is identical. F prime is equal to g prime. When you look at these, you can see that in fact the same derivative works for both functions. Their derivatives are equal, so the functions only differ by a constant. We're going to exploit this idea shamelessly when we get to chapter 5 and we study the fundamental theorem of calculus and integration. The last corollary that can be proved using the mean value theorem, well, the last one we're going to talk about, says that if you have a continuous function over a closed interval that's differentiable over the open, you can apply the mean value theorem. If the first derivative is positive for all x in the interval, then f is an increasing function. In other words, I don't have to graph it to know that it's going uphill. If the first derivative is negative for all x in the interval, then f must be decreasing over that interval. This one is discussing increasing and decreasing behavior, which we'll use a lot in the next section when we draw the graph of a function using all the techniques that we've learned in algebra and calculus thus far. Now, let's take a look at a picture which shows this. On this part to the left, you can see that the graph is going uphill and the tangent line has a positive slope at all points. That means that the sign of the derivative being positive, tells us the function is increasing. Then it reaches a relative maximum, and on the other side, it becomes a negative tangent line. It stays negative until it reaches the next relative extrema. This tells us that the tangent line must have negative slope, so the function is decreasing. Then we have an instant where the tangent line is horizontal, critical point, and then it is increasing again. Again, we're going to use this quite a bit in the next section. So what are these techniques that we'll use in the next section? Well, from algebra, we're going to use our ability to find x-intercepts and the y-intercept. And we'll also predict end behavior using the limits as x goes to infinity and the limit as x goes to negative infinity using calculus. We'll find limits on either side of a vertical asymptote, and we'll also look for the location of holes and vertical asymptotes in the graph using algebra. Then we'll use calculus to determine where it's increasing, decreasing, concave up, concave down, where the location of the relative extrema are, where the inflection points are. There are a lot of steps to producing an approximation to a graph, and we're going to use all of them to produce as accurate a graph as we can. This is important because sometimes when you look at a graph, there can be a hidden maximum or minimum that is so small it can't be detected with the naked eye. We need the techniques of algebra and calculus to pin down exactly where those points occur and what those maxima and minima values are. Join me for the next video in this series.